So make sure you take a look at your homework. And both of the due dates are set to Wednesday on those. Wednesday next week on September 2nd. Okay, so 7.2, we're going to start looking at special functions that that come up quite a bit in math. And the first one that we're going to see is the natural logarithm. And you've probably seen this before. So you probably know that logarithms are related to exponential functions in some way. And we're going to start with the natural one. It's called the natural logarithm, but its definition feels anything but natural, at least the first time you see it. So we usually write it this way, ln for natural logarithm, and then x is being plugged in. And this is going to be equal to the integral from 1 to x of 1 over t dt. And you might also remember about the natural logarithm that you can't plug in negative numbers. So this only works, or you can't plug in 0 either. This only works for positive x. Okay, so like I said, it's called the natural logarithm, but it feels totally unnatural because it's a function, but the function is defined as an integral, which feels very complicated. So what I want to do, before I just outright tell you properties, would be to just consider what the picture of this function looks like, 1 over x, or 1 over t, and then think about what its integral should be. So what the natural logarithm should be. So let's graph it. F of x equals 1 over x. You're probably familiar with it. It goes through this point, 1, 1. And over here to the left, it blows up to infinity. And then to the right, it gets closer and closer to 0 without ever reaching it. Okay, so we're going to integrate this function in order to find a natural logarithm. So what that means is we're considering areas underneath this curve. So areas down here. Let me draw on a vertical line. And our areas are always going to start being measured here at x equals 1. So the first question, what is the natural logarithm of 1? Or the first property, the way I've written it. So if we want to find the natural logarithm of 1, we have to plug in 1 into the definition. So it's the integral from 1 to 1 of 1 over t dt. What is this integral? Well, you could just remember something that you learned in Calculus 1 and tell me the answer. Or I can remind you of the geometry. So remember, an integral is actually an area under a curve. And in this particular integral, we're looking at the area from 1 to 1. So we're looking at the area of this little vertical line segment. What is that area?
0.
0. Good. So the natural logarithm of 1 is 0. You probably already knew that, but we have to make sure our definition really works the way that we expect it to from your other experience with logarithms. Okay. So another important property of the natural logarithm has to do with the number e, called the natural number. Well, I guess it has a few names. This is one name I've seen. And the letter E, I believe, comes from this guy, Euler, who was a famous German mathematician. So sometimes it's referred to as Euler's number. Okay, but do you know what E is approximately? Like what was the actual value of it? So if I said pi, you'd say 3.14. If I said E, what would you say? Maybe you don't know E. Okay, so it's about 2.7. And it's actually a button on a calculator. So probably you've used that button before and you've seen that number. No one wanted to volunteer the answer. Um, so this so-called natural number also has a very complicated definition. So it's the number such that the logarithm of the number, so the natural logarithm of e, is equal to 1. So it's the number where this integral from 1 to e of 1 over t dt is equal to 1. And I'll put a note here that e is about 2.7. And if you take a look at the curve for 1 over x, you can kind of see where it should be in order to get a total of 1. So if you integrate from here, you go here, you're not quite to 1, but then if you include a little bit more of this segment, then you're filled in this block, this area here. There are ways to actually calculate E. We won't talk about those at this moment, but that's what it's defined to be. Okay, and then my third property, we want to look at the derivative of the natural log. And this one, maybe you can tell from the definition already, but it's going to be 1 over x. And I want to consider quickly here the reason for this. So we have to go back to the definition of the derivative, not the definition of the derivative, the definition of the natural logarithm, because we're actually taking the derivative of an integral So does anyone remember from Calculus 1 how you find the derivative of an integral, or what happens? This was a really important thing, and it had a special name. No one? So one of the important ideas that you learned in Calculus 1 is that derivatives essentially undo integrals. So this derivative cancels off this integral, and you're left with 1 over x. Okay. And this had a name. It was called the, or I guess half of, the fundamental theorem of calculus. So this was one of Isaac Newton's big ideas back in the 1700s. Okay, so 3 properties. I think I'll add a bonus property here at the end. So this is another thing that we can read off from our graph. So here's the idea. The graph of 1 over x is always positive. So whenever you're finding areas, the value of that area is always going to be increasing as you move from the left to the right, because you're taking a larger piece of the graph, a positive area. So this little bonus property is this. So since what I just said is true, the value of 1 over x is always positive on that half of the graph that we're looking at when x is greater than 0, so the right half of the plane. Since we're adding up these positive areas, that means the natural logarithm is an increasing function. Okay, and why is this an important thing to note? There's an exercise on your homework, I'm pretty sure I left it on your homework assignment, where you're going to argue that, or where you're going to see that increasing functions are always one-to-one. And why were one-to-one functions important? We learned about these on Wednesday. So we talked about one-to-one functions and what was special about them. Anyone?
The horizontal line only crosses them once.
Okay, so if you wanted to test to see if a function is one-to-one, then yes, you would use the horizontal line test. But the answer that I'm looking for is that one-to-one functions are the kind of functions that are invertible. So these functions have inverses. That's going to be important for us. Okay. So with these bits of information, so 1, 2, 3, and then the fact that this is an increasing function, we can make our first sketch of the natural logarithm. We know that its value at 1, if we plug 1 into the natural logarithm, we get 0. And we know that it's an increasing function, so we can sketch it like so. So we know it's increasing, and we know that when we move further to the right, we're adding smaller bits of area, so it's going to stop increasing quite as fast the further you go over to the right, because this bit is smaller than this bit, basically. Okay, so a very rough sketch of what this looks like. Any questions so far? Okay, so the next thing I want to do is just practice some calculus with the natural logarithm. So I want to take a few derivatives here. The first one, what is the derivative of the natural log of 6? Oh, and there should be another natural log there. So what technique will we need? We'll need the chain rule. Because 6x is being plugged in to the natural logarithm. I've written it this way because this is the way you'll see it written most of the time. There aren't parentheses around anything, but when I write this next to the natural logarithm, ln, what I really mean is 6x is plugged in. So this is maybe a more formal way to write it, but mathematicians usually write it without parentheses. Something to keep in mind. Okay, so the chain rule, remember we have an outer derivative and an inner derivative. So we need the outer derivative of the natural log. So remember that was the 1 over x. But instead of writing x, I'm going to write what's inside the parentheses, the other function. And then we need the derivative of 6x. What's the derivative of 6x?
6.
Good. So this derivative is just 1 over x. So even though I had a 6 in here, inside of my natural logarithm function, it didn't actually change the derivative. So this was the basic derivative formula for natural logarithms. It's just 1 over x. If I multiply x by a number, that doesn't change the derivative. So that's the takeaway. So multiplying by a constant doesn't affect the derivative. But what happens if you have something more complicated inside of your natural logarithm, like 2x squared plus 1? Well, then more interesting things can happen. Let's see. Put a line there. Okay, so we have still a chain rule problem. We need the outer derivative for the natural logarithm. So it'll be 1 over what we find in the parentheses, 1 over 2x squared plus 1. And then we need the inner derivative. What's the derivative of 2x squared plus 1?
4x.
Right. So when you have a more complicated function inside of your natural logarithm, you do get some extra stuff from your inner derivative. It's not just 1 over x anymore. Okay, any questions before we do the third example?
Is that how you would leave it like on a test, or would you want us to simplify it more?
You can leave it like this unless I explicitly tell you to simplify. So in calculus 2, I'm wanting you to practice your calculus skills, not your simplifying skills. Okay. So this is going to be our last example for today, it looks like. I want to find the derivative of the natural log, and now I've taken the absolute value of x. So we get the outer derivative, 1 over what's inside. So it's 1 over the absolute value of x. And then we need to multiply by the derivative of the absolute value of x. Does anyone remember what that derivative is? So remember what the absolute value function looks like is this. So if you're on this half of the graph, it's a line with slope -1. And if you're on the right half of the graph, it's a line with slope +1. And the easiest way to write that is like this. It's x divided by the absolute value of x. Which works out to a piecewise function, 1 for x greater than 0, and -1 for x less than 0. So in case you didn't remember that, that's how that works. So here's the derivative after we plug in. So we have 1 over the absolute value of x times x over the absolute value of x. Okay, and now I do want to simplify this just a little bit. the absolute value of x times the absolute value of x is actually x squared. We can drop the absolute values. And the reason for that is that when we square a negative number or a positive number, it always comes out positive. So we can just drop the absolute values. And that helps us simplify. This is just 1 over x. Okay. So we will stop there. Except that I want to, and you can go ahead and leave now if you need to. I just want to write down my conclusion. Since the derivative of the absolute value was 1 over x, that's just the original derivative. What this means is that the derivative of the natural log of minus x is also 1 over x when we're plugging in negative numbers. So negative x, when x is negative, is the absolute value. That's the reason why. Okay, so if there aren't any questions here at the end, I'll go ahead and let you go.